Welcome back. Last time, we used the first derivative as a diagnostic tool, critical points, the first derivative test, Fermat's theorem, Rolle's theorem, and the mean value theorem, the workhorse that bridges instantaneous and global behavior. Today, we go one level deeper. We take the derivative of the derivative. The second derivative, f double prime, doesn't tell you which way the function is going. It tells you how the function is bending while it goes. That single extra piece of information unlocks concavity, inflection points, a faster classification test for extrema, and the physical interpretation of acceleration. We'll build it all from scratch, work 2 examples, and close with the full curve sketching procedure that combines everything from the last few episodes into a single diagnostic pipeline. Let's go. Definition. The second derivative of f is just the derivative of the first derivative. Differentiate f to get f prime, differentiate f prime to get f double prime. The notation, f double prime of x, or in Leibniz notation, the second derivative of f with respect to x. In physics, you'll often see 2 dots above the variable. Same object. Quick example, f of x equals x cubed. F prime of x is 3x squared. F double prime of x is 6x. The first derivative measures the slope of the function. The second derivative measures the slope of the slope, that is, how the slope is changing. And that change in slope is exactly what we mean geometrically by curvature, by bending. The sign of f double prime is going to be the key. Positive bends one way, negative bends the other. Concave up. We say f is concave up on an interval if f double prime is positive throughout that interval. 3 equivalent ways to think about it. First, geometrically, the curve bends upward. Picture a smile, a U shape, a bowl that holds water. Second, in terms of tangent lines, every tangent line you draw to the curve sits below the curve. The curve curves up and away from its tangent. Third, in terms of the slope, f prime is increasing. The function might still be going down. Concave up doesn't mean increasing, but its slope is getting more positive over time. The canonical example is f of x equals x squared. The second derivative is 2, which is positive everywhere. The parabola opens upward, holds water, and its tangent lines all sit underneath it. Concave up on all of the real line. Concave down is the mirror image. F is concave down on an interval if f double prime is negative throughout. Geometrically, the curve bends downward, a frown, an arch, an upside-down bowl that doesn't hold water. Tangent lines lie above the curve dips away from its tangent, and the slope f prime is decreasing, getting more negative or less positive as x increases. Canonical example, f of x equals minus x squared, second derivative is minus 2, negative everywhere. Parabola opens downward, concave down on all of the real line. Smile, f double prime positive. Frown, f double prime negative. That's the mnemonic. Picture. On the left, a parabola opening upward. Concave up, f double prime positive. The red tangent line at the marked point sits visibly below the blue curve. The curve smiles, and the tangent lives underneath the smile. On the right, a parabola opening downward. Concave down, f double prime negative. The red tangent line at the marked point sits visibly above the blue curve. The curve frowns, and the tangent floats above the frown. This is the geometric content of concavity in one picture. Smile below, frown above. If somebody asks you which way is the curve bending, look at where the tangent line goes. Below means up, above means down. Inflection points. An inflection point is a place where the concavity of the function changes. The curve was smiling, and now it's frowning, or vice versa. The curvature flips sign. Necessary condition, at any inflection point C, either f double prime of C equals 0 or f double prime of C fails to exist. Both kinds are possible candidates, but this is necessary, not sufficient. You also need the sign of f double prime to actually change as you cross C. The standard counter example is f of x equals x to the fourth at x equals 0. F double prime is 12x squared, which is 0 at 0. But 12x squared is non-negative everywhere. It touches 0 at the origin and bounces back up. There's no sign change. So 0 is not an inflection point of x to the fourth, even though f double prime vanishes there. The function is concave up on both sides. So find places where f double prime is 0 or undefined, then check whether the sign actually flips. Picture. The classic cubic, y equals x cubed. To the left of 0, the curve is concave down, it frowns. To the right of 0, the curve is concave up, it smiles. At the origin, marked with a red dot, the concavity flips. That's an inflection point. We can confirm it algebraically, f double prime of x equals 6x. For x less than 0, 6x is negative, concave down. For x greater than 0, 6x is positive, concave up. At x equals 0, f double prime equals 0, and the sign flips as we cross. True inflection point. The tangent line at the origin happens to be the x-axis itself, slope 0, and it crosses through the curve rather than staying on one side, which is the visual signature of an inflection point combined with a horizontal tangent. The second derivative test. Suppose C is a critical point of f, with f prime of C equals 0, so the tangent line at C is horizontal. Now look at f double prime at C. 3 cases. Case 1, f double prime of C is positive. The graph is concave up near C. A horizontal tangent in a smile means the curve goes up on both sides of C, so C is a local minimum. Case 2, f double prime of C is negative. The graph is concave down. A horizontal tangent in a frown means the curve goes down on both sides, local maximum. Case 3, f double prime of C equals 0. The test is inconclusive. The graph is too flat at C for the second derivative alone to tell you what's happening. In that case, you fall back to the first derivative test, check the sign of f prime on either side of C. The second derivative test is faster when it works. You only need to compute f double prime at the one point C, no sign chart required. When f double prime is 0, you don't get lucky and you have to go back to the slower test. First worked example. Classify the critical points of f of x equals x cubed minus 3x using the second derivative test. This is the same function we classified last episode using the first derivative test. Let's see how the second derivative test compares. Compute f prime, 3x squared minus 3, set equal to 0, x equals plus or minus 1. 2 critical points. Now compute f double prime, differentiate again, 6x. Evaluate at each critical point. At x equals minus 1, f double prime is minus 6, negative, local maximum. At x equals 1, f double prime is 6, positive, local minimum. Done. No sign chart, no test points, just plug in. Same conclusions as the first derivative test gave us, max at minus 1, min at 1. As a bonus, set f double prime equal to 0, 6x equals 0 gives x equals 0. Sign of f double prime is negative on the left, positive on the right, true sign change. So x equals 0 is an inflection point. The curve is concave down on minus infinity to 0, concave up on 0 to infinity, with the inflection right at the origin. We now have the complete shape, rises to a peak at minus 1, 2, descends through the inflection at the origin, continues down to a valley at 1, minus 2, then climbs again. Second example, and a cautionary one. Classify the critical point of f of x equals x to the fourth at x equals 0. The derivative is 4x cubed, which equals 0 at x equals 0, so 0 is a critical point. The second derivative is 12x squared. Evaluate at 0, 12 times 0 squared equals 0. The second derivative test is inconclusive. This is the too flat to decide case. The graph of x to the fourth is so flat at the origin that the second derivative can't see the curvature, but that doesn't mean there's no extremum, we just have to use a sharper tool. Fall back to the first derivative test. Sign of f prime to the left of 0, 4 times a negative number cubed is negative. Sign of f prime to the right of 0, 4 times a positive number cubed is positive. Sign goes from minus to plus across x equals 0, so x equals 0 is a local minimum, with value f of 0 equals 0. And in fact, it's also the global minimum of x to the fourth. The lesson, f double prime equals 0 at a critical point, doesn't mean not an extremum. It means the second derivative test has nothing to say. Use the first derivative test instead. The physical interpretation. Take s of t to be the position of a particle at time t. Then s prime of t, the first derivative, is the velocity. How fast the particle is moving, with sign indicating direction. Positive velocity, moving right. Negative velocity, moving left. The second derivative, s double prime of t, is the acceleration. How the velocity is changing. Positive acceleration means velocity is increasing, but that doesn't always mean speeding up. If you're moving to the right and acceleration is positive, yes, you're speeding up. But if you're moving to the left with negative velocity and acceleration is positive, you're actually slowing down. The positive acceleration is decelerating your leftward motion. Sign and direction matter. Concavity of the position function is exactly acceleration. Concave up, positive acceleration. Concave down, negative acceleration. Zero acceleration is constant velocity, no net force. And Newton's second law, force equals mass times acceleration, becomes capital F equals m times s double prime of t. The whole of classical mechanics rides on this second derivative. One more refinement worth noticing. There's a difference between velocity and speed. Velocity is signed, it's s prime. Speed is the absolute value of velocity. You speed up when velocity and acceleration share a sign and slow down when they have opposite signs. So s double prime alone doesn't tell you speeding up or slowing down, you need both s prime and s double prime. Sign agreement of the two derivatives, speeding up. Sign disagreement, slowing down. This is exactly the same as the 4 combination table we just looked at, now wearing physics clothes. The full curve sketching procedure, combining everything from the last several episodes. Step 1. Identify the domain. Where is the function defined? Are there forbidden inputs, division by 0, square roots of negatives, logarithms of non-positives? Step 2. Find the intercepts. Where does the graph cross the axes? Solve f of x equals 0 for the x-intercepts. Evaluate f of 0 for the y-intercept. Step 3. Find the asymptotes. Vertical asymptotes where the function blows up. Horizontal asymptotes from limits at plus and minus infinity. Oblique asymptotes for rational functions whose numerator is 1 degree higher than the denominator. Step 4. Compute f'. Find the critical points where f' is 0 or undefined. Step 5. Sign chart of f' to determine where the function is increasing and where it's decreasing. Step 6. Compute f'. Find candidates for inflection where f' is 0 or undefined. Step 7. Sign chart of f' to determine the intervals of concavity and confirm that each candidate inflection actually has a sign change. Step 8. Combine everything into a sketch. Plot the critical points and inflection points, connect them with curves of the correct slope and curvature, and make sure the asymptotic behavior matches. That's a complete sketch. Slow on the first pass, fast with practice. The two derivatives encode independent information. The first tells you direction, the second tells you bending. 4 combinations. f' positive, f' positive, function is increasing and concave up. The slope is positive and getting more positive, accelerating upward. f' positive, f' negative, increasing but concave down. Still going up, but slope is decreasing, like a ball thrown upward that's slowing as it climbs. f' negative, f' positive, decreasing but concave up. Going down, but the descent is slowing, like a parachute opening. f' negative, f' negative, decreasing and concave down. Going down and getting steeper, free fall, accelerating toward the ground. These 4 patterns cover every smooth function locally. Direction from f', bending from f'. The information is genuinely independent. Knowing one tells you nothing about the other. A few pitfalls to keep on the table. First, f' equals 0 at a point does not, by itself, guarantee an inflection point. You also need the sign of f' to flip as you cross the point. The function x to the 4th is the standard example. f' is 0 at the origin, but never changes sign. No inflection. Second, when the second derivative test returns 0, the function might still have an extremum, or it might not. Silence isn't a verdict. Use the first derivative test instead. Third, concave up does not mean increasing. E to the minus x is concave up everywhere. Its second derivative is e to the minus x, which is positive, but it's also decreasing everywhere. Direction and bending are separate. Fourth, inflection points can also occur where f' is undefined, not just where it equals 0. The cube root of x has f' undefined at 0, but the concavity flips from up to down across that point, so the origin is still an inflection. Fifth, critical points and inflection points are generally different points on the graph. A critical point is where f' is 0 or undefined. An inflection point is where f' changes sign. They don't have to overlap. In x cubed, they happen to coincide at the origin. Both f' and f' are 0 there, but that's a special feature of x cubed, not a general rule. Where we landed. The second derivative f' is just the derivative of the first derivative, and its sign tells you how the curve is bending. Positive f', concave up, smile, tangent below the curve. Negative f', concave down, frown, tangent above. Inflection points are places where the concavity flips. Necessary that f' is 0 or undefined there, and necessary that the sign actually changes. We saw that x to the 4th has f' equal to 0 at the origin but no inflection, because the sign doesn't flip. The second derivative test classifies a critical point quickly. Positive f' means a local minimum, negative means a local maximum, 0 is inconclusive. We worked x cubed minus 3x with the second derivative test, max at -1, min at 1, inflection at the origin, and then x to the 4th at 0, where the second test gave us nothing and we had to fall back on the first test to get local minimum. Physically, the second derivative is acceleration, s is position, s' is velocity, s" is acceleration, and Newton's second law bridges back to mass and force. We sketched the full curve, sketching pipeline, domain, intercepts, asymptotes, f' and its critical points, f" and its inflection points, then plot. Direction comes from f', bending comes from f', the two are independent. Next time, episode 13, optimization, applied maxima and minima. We take everything we've built and use it to solve real problems. Minimum cost cans, maximum area fences, cheapest cylinder of fixed volume. The first and second derivative tests turn into a problem-solving strategy. See you in episode 13. Concavity is the universe telling you what the function is doing while it's busy doing something else. Curves that smile carry tangents underneath. Curves that frown hold tangents above. The like button is concave up. It holds the entire weight of the recommendation algorithm on its tangent line. Press it and you become the inflection point. Thanks for watching. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.